Hi everyone, welcome back to another video. And last time in our stat series, we talked about alpha and confidence levels and talked a lot about type 1 error, but we're going to flip over to the other side today talking about power and beta and what this means for your hypothesis testing and for your statistics in general. So let's review a little bit because it's been a minute since we talked about any of this. So if we have our 2x2 table, we've got our H naught is equal to the null hypothesis. So if the null hypothesis is true and we do not reject it, that is a correct conclusion. And that, as we discussed last time, is the confidence level and is calculated by 1 minus alpha. And then if we have our null hypothesis is true and we reject it, when we shouldn't reject it, that is a type 1 error, and the probability of achieving a type 1 error would be alpha. And so that's where we got that. If you have questions about alpha and confidence level, go back and watch that video, because today we're going to move on to talking about power and beta, which is kind of similar in concept, but just the other side, talking about type 2 error. So if we review a little bit, if our null hypothesis is false, so the assumption that there's no difference is false. So there is a significant difference. And so if we have a difference, the null hypothesis is false, but we do not reject it. So we fail to recognize a difference. This is a type 2 error. And of course, if our null hypothesis is false and we do appropriately reject it, that is a correct conclusion. So we have some numbers to figure out exactly what our risk of type 2 error is, and this is beta. So beta is kind of similar to alpha, but with regard to type 2 error. So beta is our probability of committing a type 2 error with our study. So the probability that our null hypothesis is false and that we will not reject it. We will fail to reject it when we should reject it. So that's our probability there. So then power relates to the test and our test ability to detect a significant difference when there is one. This is the probability that our test is good enough to detect a significant difference in the case that there is one, and we solve this by 1 minus beta. So we take 100% and we subtract the probability of our type 2 error. So with this, we are risking type 2 error. Just like when we were calculating the confidence level, we were risking a type 1 error. So some things that we need to address. So obviously, when I'm doing a study, my goal is to detect any significant difference and then make sure that we're not ruling in possibilities that are not true. We want to have as accurate of study results as possible. But I do want to make sure that I am capturing enough of the population so that if there is a difference, I pick it up. I want to be sensitive enough to not miss a significant difference. Because even if I want to avoid type 2 error, right, I don't want to be so conservative in my approach that I falsely hold on to a null hypothesis when it's not true. That could lead to me not intervening when I should. So it's important that we kind of balance these out, and there are values that we accept for power and for what risk we're willing to take with type 2 error. So this is the question. What risk of error am I willing to accept to detect a difference? So the goals of any study, I want to have a high level of power. I want to be able to detect any significance that is present. I also want to have a high confidence level. I want the ability to rule out answers that are not there. I want to make sure I'm not prematurely rejecting the null hypothesis. So with that, of course, I want to decrease my probability of type 1 error, and I also want to decrease the probability of type 2 error. So what number can we use for power to achieve all of these goals to the best of our abilities? And the most commonly accepted value for power is 80%. And you might think, why 80%? Why are we allowing, if 80% is the probability of detecting a significant difference, that leaves us, if we subtract 80% from 1, we get 20%. So that is a 20% chance of a type 2 error. That sounds really high, right? Because last time when we talked about alpha is usually at 5%. So a 5% chance of a type 1 error. So why are we willing to accept a 20% chance of type 2 error? And this relates a lot to what we need to do in order to increase power. Why are we not raising the power to 90%? Because if I had power of 90%, I would have only a 10% chance of type 2 error. But the problem is, I'm now risking not picking up a difference that's there. And something else that happens here when we do this, when we increase power, we decrease beta, which is great. We want to decrease beta as much as possible, but we also increase alpha. So in our attempt to decrease beta, we will, by default, by this direct relationship, we will increase alpha. So we have to weigh this out. What is more important to us? Is it more important that I avoid type 1 error, or is it more important that I avoid type 2 error? And that could be a whole separate video about why we prioritize type 1 error over type 2 error. But we can talk today a bit about the factors of how we can influence power. What variables go into determining power, and how can we manipulate this? So the first thing is effect size. So if you have a study, let's say we are measuring the effects of caffeine on test grades, something simple like that. So I could, in an attempt to really separate out my control group from my experimental group, let's say I only gave the experimental group a very small amount, like 5 milligrams of caffeine. You're probably not going to detect much of a difference, right? Because you might not even get the effect of the caffeine on that population. It might not be easy to differentiate. So if I increase the dosage of the caffeine to 300 milligrams, you're more likely going to see a difference. So effect size can impact power, because if there is more of a difference that is detectable, of course, your test is going to be more likely to detect that difference. The next one is sample size. And this is one that factors into why we choose 80% versus 90% for power, because in order to increase power, in order to detect a significant difference, you can do that by increasing your sample size. The more people you have in your study, the greater chance you are going to achieve a bell curve. You're going to achieve a normal distribution, because the more people you add, the more people you have that can meet every stage of that spectrum. So increasing sample size would increase power, but that's not always practical. Of course, I would love to be able to do a study where we had the entire population on Earth to study, but that's not reasonable. And you have other variables playing in there as well. But sample size can influence power. And if you cannot increase your sample size to, say, 2,000 people, well, you're going to have to settle then for a decrease in power and a greater likelihood of error. So that's one factor. Significance level. As I mentioned, alpha is directly related to power. As I increase power, I increase alpha. So if I say that alpha is instead of 0.5%, I say it's 1. So 100%, or 10%, sorry. This is going to be influential, because if I have a 10% chance now, if we go back, look at our alpha, 10% chance of type 1 error versus a 5% chance, I'm willing to accept more error in that compared to if it was 5%. So in accepting more type 1 error, I can raise my power. I'm more likely to detect a difference because I am determining that 10% is good enough to be a significant difference. Measurement error, of course. Precision and accuracy. If I have error in my study, if I have error in the way I measure my data, that could increase power because I could potentially detect a difference that's not there. That is influential. And then finally, and I'll get into this in other videos because I think this one's hard to wrap your mind around, but one versus two-tailed tests. And I have the graphs here. The one on the left is the one-tailed test, and then the one on the right is the two-tailed test. So if I put all 5% of my alpha on one side of the graph, I'm more likely to achieve a value within that larger area on that side of the graph, compared to if I have 2.5% on each side, I'm less likely to detect a difference depending on if I'm looking for the 2.5% versus the 5%. So using a one versus a two-tailed test can influence your power and can be a reason why you would either detect or not detect a significant difference. So I hope that this made sense. I hope that the stats are starting to click a bit more, and we're going to go farther in future videos into what tests we would use, because now we've established our variables, right? So we've established our probabilities, we've established our risk of error. So now I think we can actually start getting into how do I demonstrate causality? How do I prove something to be causal or not? We're going to get into that later. Thank you all for joining me, and stay curious. I will see you all in the next one.